Okay, let's go ahead and take a look at this concept called power in case you missed class or if you just need to refresh your memory on this concept. This video is for you. Okay, so power. Oftentimes when people think of powerful athletes or powerful cars, it's really a measure of like how quickly something is done. A very powerful sprinter can run the 100-meter dash more quickly than someone that's less powerful. A very powerful car can get up to speed in a very short amount of time, as opposed to one that takes my first car I bought, 0 to 60 miles per hour in 20 seconds. Not very powerful. So power is really much a rate idea. Power is a measure of the rate at which work is done, or we could say the rate at which energy is transferred. And again, that goes back to our definition of work, not just being a force through a distance, but work is a transfer of energy between objects. Whether the person walks or runs up the stairs, the amount of work he does is the same. He's essentially having to lift his body against the force of gravity. Whether or not he runs or walks up the stairs, he does the same amount of work. What's different there is the amount of power he or she develops as work is being done more quickly. Now I think about my car when I go 0 to 60. If I want to do that really quickly, I step on the gas and the car engine revs to a really high RPM. If I run up the stairs, it's not the engine that's revving, it's my heart. My heart starts to beat a lot more quickly, and that's just evidence of the fact that I'm transferring energy more quickly than when I'm walking. Let's go ahead and do some equations here. Power, again, is work divided by time. So let's go ahead and write that here. Power, work over time, or I could think of that as energy transferred per unit time. I'd like to take a moment and try to develop another equation. Instead of work divided by time, I could say that work over time could actually be thought of as force times distance over time, recognizing that work is force through a distance, and then I could rearrange the d and the t and sort of think of that as force times velocity. Okay, so if I just sort of regroup the distance and time together, I could say that the average power of maybe an athlete or of a car is the amount of force that they're exerting multiplied by how fast they're moving. And so a couple of different ways for us to quantify power. Let's take a look at the units. The SI unit for power, the International System of Units that we've all agreed to use, is the watt. 1 watt is 1 joule of energy, 1 joule of work, 1 joule of energy transferred in 1 second. So we could say 1 watt will give it a 1 joule per second. Now a more familiar unit for you, if you ever work on cars or know anything about car engines, the horsepower is a more common unit for us to describe power. Originally developed or defined based on sort of an average work done, or the average power developed by a horse plowing the fields. It's not very scientific, maybe depending on what kind of food that horse ate for the day. They might not be as powerful, so it's certainly not a very scientific definition, but 1 horsepower is now equivalent to 746 watts. And this again is just a conversion, trying to take something from the old days and put it into something a little bit more scientific for the new days. So 746 watts for each horsepower. Let's take a look at Michael and Jim. So Michael and Jim are both lifting some weights here. And you can tell by looking at this that it appears that Michael is the more powerful athlete. He is doing a certain amount of work, but he does it very quickly, whereas Jim, not as powerful, does the same amount of work, but does it in more time. How much work does each person do? Well, work is, again, force times distance. And they both exert 100 newtons of force, and they do that through a distance of 2 meters, so they both do the same amount of work. That's 200 joules of work. Now, if I want to talk about power, power is a work per unit time. So if I want to do the developed or determine the power that Michael develops, let's go ahead and write that with subscripts. So the work that Michael does is 200 joules. But he does that in 1 second. So he developed 200 watts of power. When I look at Jim, I see that Jim did the same amount of work, But it took longer to do that. So 200 joules in 10 seconds means that he developed power at a rate of 20 watts. Okay, so same amount of work, but different powers because they did that work at different rates. Now, oftentimes when we start looking at power and we look at the units of watts, people think of light bulbs because we see that standard light bulbs, you go and buy them at the store, they often have a 100-watt rating or a 25-watt rating. Some of the newer bulbs that you'd see, these green bulbs, are all listed by their wattage. All bulbs convert electrical energy to other forms. Their power, measured in watts, is simply describing the rate at which that conversion takes place. So when I say 100 watts, I'm saying 100 joules per second of energy. And again, that's the electrical energy that's flowing through this bulb to be able to generate that light. That light bulb is using 100 joules every second. 25 joules every second, 30 joules every second. Their wattage, again, indicates the rate at which the conversion is taking place. Now, besides the process through which light is created, the bulbs differ in their efficiency as well as their life expectancy. And when you go out and you start buying your own light bulbs to maybe light your home or apartment, you'll see that you'll start to pay more attention to the cost of these things, how long they're expected to last, and also how much energy they're using. Let's talk a little bit about efficiency for these light bulbs. Now, I just did a quick little Google search on this, and let's go ahead and pull that up because it's been a while since I've looked at efficiency. So let's see. 100% efficient light bulb would convert all electricity to light and not produce any heat at all. That's not really realistic. Ask visitors, I'm not sure what this site is here. It's an educational site, probably reliable. The LED bulbs are about 90% efficient. A compact fluorescent bulb is about 85% efficient, and an incandescent bulb is only about 10% efficient. It's not very good efficiency for those things. Let's go ahead and put some of these numbers down here. So the incandescent light bulbs are only about 10% efficient. That means 90% goes to heat and 10% goes to light. And of course, usually we use our light bulbs to generate light. We're not so interested in having the heat as a byproduct. Unless, of course, I'm using these for like an easy bake oven or something, then no problem. Give me the 90% heat. But mostly it's for light. Now, the 30-watt fluorescent bulbs, they said that these were in the neighborhood of 85 to 90%. And I think the LED bulbs, they said, was 90% efficient. So these things, only 10% going to heat, and the other 90% going to light. Okay, so the LED bulbs, the LED stands for light emitting diode, much more efficient. So we end up using a lot less energy to provide lighting for our home. Let's go ahead and take a look at this problem down here. Compare the electrical energy needed to provide lighting for 1 hour using the 100-watt bulb versus the 10-watt LED bulb. Okay, so again, if this is more efficient, then I should be able to provide the same amount of light just using less energy. Let's go ahead and compare those energies. I'm going to do that right here. Power, we said, was energy per unit time. Let's rearrange this to give energy. I just simply multiply power times time. For the 100-watt, I have 100 joules per second. That's going to be operated for an hour. Well, let's put that in as 3,600 seconds, and I'd see that that is 3,600,000 joules. So it's a lot of energy going through that light bulb every hour. Now, if I looked at the 10-watt, you would see everything's the same except the rate at which I'm using that energy is 1/10 as great. That means I need 1/10 the amount of energy. So if I use a 10-watt light bulb versus a 100-watt light bulb, I'm using 10 times less energy, and of course I pay for that. So the less energy I use, the less it affects me in my pocketbook. Let's go ahead and take a look at a few problems here. Wayne pulls a 305 Newton sled along a snowy path by pulling horizontally on a rope. Wayne pulls with a force of 42.3 newtons. The sled moves 16 meters in 3 seconds. How much work does Wayne do, and how much power does Wayne produce? So first thing you might want to do is just make a little list of these values. Force is 42.3 newtons, or is it 305 newtons? I see two different Newton values up there. Which one is needed? And again, if you think about what's happening, with this particular problem, he's not lifting this thing up, he's actually pulling it this way. So the force that he's exerting is here, that's the 42.3 newtons. If he were lifting it, then he would have to be going this way with it, but he's not, he's going this way. So even though I was given 305 newtons, that doesn't come into this particular problem. The distance he moves, this thing is 16 meters, and the time is 3 seconds. So now I have a little list there, and I can use that to help answer some of these questions. Work we know is force times distance. So if I take the 42.3 newtons and I multiply that by the 16 meters, I get an amount of work that's 676.8 newton meters, or I could say 676.8 joules. Power is a work per unit time idea. We just calculated that he does 676.8 joules of work. That takes him 3 seconds. So I just simply take that number divided by 3, and I get that he's doing work at a rate of about 225.6 joules per second, or watts. While loading a moving truck, a person lifts 25 boxes weighing an average of 60 newtons, and he lifts each box approximately 1.3 meters. If the task takes 3 minutes, what average power is developed? Again, we might take a little, make a little list here. The force due to gravity is 60 newtons, and that's per box, right? That's per box. He is lifting those 1.3 meters for each one, and the time is 3 minutes. I'm going to put that down in seconds, since the unit for power is watts, and that's joules per second. I'm going to make sure that my unit is my unit for time is seconds. Let's go ahead and determine the power as work divided by time. I don't have work directly, but I can do that as the force due to gravity that he has to exert to lift those things times the distance that he's lifting those divided by the time. I see I have 60 newtons. Each one is 1.3 meters that I need to lift it, and I divide that by, well, let's see, I don't know how long it takes to lift one box. I only know how long it takes to lift all 25, so I'm going to go ahead and do 180 seconds and say that that's 25 of those boxes. So I'm going to have the numerator represent the total work he does in lifting all 25 boxes, and then divide that by the time. And I see that he's doing work at a rate of 10.8 joules per second, or about 10.8 watts. Let's take a look at number 3. My car has a mass of 2,100 kilograms. The total of all opposing forces acting on my car while traveling at highway speeds is about 29 meters per second. It's about 450 newtons. How much power must my car's engine develop to continue moving at this speed? Let's review Newton's first law. An object in motion stays in motion. An object at rest stays at rest unless acted on by an unbalanced force. This car, in order to travel at a constant speed, must continue to exert forward force. If I take my foot off the gas pedal, I immediately start to slow. And the reason for that is that I have some opposing forces that my engine must do work to be able to overcome. So I'm going to go ahead and say that this is the force from the engine that's turning the wheels, right? The engine turns the wheels push back on the ground pushes forward on the car, right? So this is the ground pushing forward on the car. That comes from the engine turning the wheels, and so forth. It's a Newton's third law idea. Now, the reason I have to continue to exert force forward is because I have some force of resistance, which I'm measuring here to be 450 newtons. Okay, the weight force and the upward force, those normal force and weight force, don't do any work here. If I want to determine the power that my engine develops, I'm going to use the force that my engine produces multiplied by the velocity that my car is moving. So 450 newtons, and because these two have to be the same, moving at 29 meters per second gives me a power of about 13,050 watts. Now, I'd probably rather look at that in horsepower, since horsepower is typically the unit that I would use to describe engine power. So let's go ahead and divide that by 746 watts per horsepower, and we get that's about 17.5 horsepower. Now, for those that know cars, you know 17.5 horsepower is not that much. I don't need a lot of power to be able to move at highway speeds. Where I need my power is to accelerate my car from maybe 0 to 60. If I take my standard car, the one I bought when I was 16 years old, 0 to 60 in 20 seconds, not very powerful. If I want to be able to do that much more quickly, 0 to 60 in 8 seconds, I'm going to have to do that work much more quickly, and that's really where I need that power. I don't need a lot of power on the highway. Let's go ahead and take a look at those last two problems. Here I have a person doing some chin-ups. He weighs in at 750 newtons. He's doing some chin-ups. His arms are 62 centimeters in length. He does 8 chin-ups in 23 seconds. How much work does he do against gravity? How much power does he produce? Force due to gravity, 750 newtons. That's his weight. His arms are 62 centimeters in length, but I'm going to put that in meters since the SI unit for energy is joules, and that's Newton meters. I want to make sure those units are right. Now the time it takes is 23 seconds, and I should put that N. The number of chin-ups this person is doing is 8. That will help me keep track of the total amount of work. So let's see, work is force times distance. He's having to lift himself 750 newtons of force that he's exerting upward to lift his body, and through a distance of 0.62 meters. Right? So as he's lifting himself, he's doing positive work. And let's see, if I want to determine the total work, then I'm going to take that and multiply that by 8 to get the total work. And I'm getting about 3720 joules. Well, certainly as he lowers himself, he's probably exerting an upward force so he doesn't go flying down into the ground really quickly, but now his distance his motion is downward. So as he's lowering himself, he's doing negative work, but let's just talk about the work he's doing against gravity. 3720 joules. Now the power that he's developing, we take that 3720 joules and divide that by the 23 seconds for all 8 of those, and that's about 161.7 watts. Okay, last one, number 5. Person whose mass is 65 kilograms runs up a flight of stairs in 7.2 seconds. There are 18 steps, each being 14 centimeters high. How much work does he do against gravity? How much power does he produce? Now I have the staircase over here. You can see that the staircase is very much like an inclined plane. Let's go ahead and draw that over here for a second. You remember that an inclined plane helps us do work by reducing the amount of force at the expense of distance. So if this person's running up the steps, you might be able to exert a small force through a much larger distance. But it would be the same amount of work if we assume 100% efficiency here of exerting a much larger force, which would be his full weight, through a smaller distance, which would be the height of those steps. So the same amount of work in either case. I think it's going to be easier for us to determine the work using these here. He has a mass of 65 kilograms, so the weight force is 65 times 10. He weighs 650 newtons. If I could just figure out how tall these stairs are, then I could just figure out the work he's doing is that force times that distance. Let's see, that distance is 18 steps, and each one is 0.14 meters. So the total distance is 2.52 meters. So now I have enough to be able to calculate the work that he does. He is 650 newtons of weight, and he's lifting himself 2.52 meters. And that work is about 1,638 joules. And if I want to determine the power, I simply take that amount of work and divide that by the amount of time that it takes him to do that. And we get about 227.5 watts. So there we go, 5 problems showing you how we might use the power equations and how it's related to work. And that completes the lesson for power.